Hi. In the first two segments of this lecture, we first looked at how to understand recursive definitions in general, then we looked at recursion over the natural numbers, and finally over domains constructed inductively through rules or generators. However, we still haven't discussed the problem from the beginning of the lecture using the example of the Ackermann function, which performs recursion over two natural numbers. How do we know, for anything but the simplest cases of recursive functions, that they are well defined and will terminate? This of course includes structural recursion from the previous segment. In this example, operating on strings constructed by rules. With functions performing recursion on domains like that, we need to generalize and formalize our intuition that recursion is okay if the recursive function only calls itself on quote-unquote smaller argument values and will eventually run into a base case. This is what this segment is about. The basic idea is pretty straightforward. Given a recursive function, if we want to show that it always terminates, we must find an order, possibly a partial order, that orders the elements of the function's domain in such a way that two things are simultaneously true. First, the function always calls itself only on a quote-unquote smaller argument according to that order. That is, the arguments of the recursive calls are strictly smaller than the argument received by the call they are made in. Factorial of 4 calls itself recursively with factorial of 3. Fibonacci of 20 makes recursive calls on 19 and 18 and so on. Whatever order we plan on using to arrange the elements of the domain of a recursive function, and whatever the nature of that domain, in order we intend to use for showing that the function terminates will have to be chosen so that calls are only made on smaller argument values. Second, the order has to be such that given an element in the domain, you cannot find smaller and smaller elements ad infinitum. Just as less than on the natural numbers, every descent along that order will eventually have to end at an element for which there is no smaller element. These quote-unquote minimal elements of our order are the base cases of our generalized recursion. It turns out this is just what a so-called well-founded set is. A set with an order, that is a partially ordered set or poset, such that every non-empty subset has a minimal element. It is equivalent to, and could also alternatively be defined as, a set with an order in which there are no infinite descending chains, which is precisely how we want to generalize our intuition about recursion and when it terminates. In order to understand this definition properly, it is important not to confuse minimal and minimum elements. A minimal element of a set is one such that there are no elements of the set that are smaller than the minimal element. A minimum is an element that is smaller than all the others in the set. Take, for example, the power set of the set ABC without the empty set, ordered by strict set inclusion. This is the Hasse diagram of the set. Note that it does not have a minimum element, but three minimal ones, the three singleton sets at the bottom of the diagram. Now let's look at some subsets of this set. This one, too, has no minimum, but two minimal elements. Again, the two singleton sets. The same is true for this one. It has no minimum, the singleton set containing just B isn't smaller than the set AC because it is not a subset of it, but two minimal elements, the singleton set B and the set AC. This subset actually does have a minimum element, which then is of course also its only minimal element, the singleton set containing C. Finally, all the elements of this set are minimal, and of course there is no minimum. Take a look at these posets and determine which of them are well-founded. And these are the answers. With this, we can precisely define when a recursive function is well-defined. If its domain can be well-founded, such that the computation of the function value for any input will only ever depend on recursive calls on values that are smaller, according to that order of the well-founded domain. But how can we use this in practice? How do we apply these ideas to, for example, the Ackermann function? We begin by identifying the inequalities that must hold for any order to be useful to us in analyzing the function. We do this by looking at the recursive calls it is making. For example, this call, which is called when the first parameter to A is greater than 0 and the second is 0, calls A again with m minus 1 and 1. So that pair has to be strictly smaller than the pair m0. The other two recursive calls happen in the catch-all third case for arbitrary pairs of non-zero m and n. The inner call is on m and n minus 1, while the outer call is on m minus 1 and whatever the inner call returns. At this point we don't know what that might be, so we just call it x and make no assumption about its value. These two calls give us more inequalities that must hold in our order. So all in all we end up with three inequalities that describe what the Ackermann function does to its parameters as it performs its recursion. So which order would make n times n squared, well-founded, and also make these inequalities true? The order less than lex, the lexicographical order we saw earlier. As an exercise, take a look at the buggy version of the Ackermann function and see how it fails to come out as well defined when analyzed by this method.